course on rheology, we have discussed several times the microstructure of complex materials, and we have seen that the microstructure plays a crucial role in determining the rheological response. And we have always tried to understand the overall rheological response by trying to relate to whatever may be the microscopic mechanisms. And in the last 2-3 decades, there has been significant progress in trying to make models for rheology based on the microscopic picture itself. Given that microstructure has such a relevant role and such a crucial role to play in determining rheology, it becomes more insightful if we can develop a model at the microscopic scale. We decide what are the dominant mechanisms which contribute at the microscopic scale, and then we have to have tools to then take the microscopic picture to the bulk scale, so that we can get the rheological response. And so, in this segment of the course, we will discuss the microscopic models for rheology. Specifically, what we will do is initially just review some key concepts of statistical mechanics. Going from the microscopic scale to the rheological response, we require tools of statistical mechanics, so that we can average the behavior which is observed at microscopic scale to obtain the bulk response. We will discuss some aspects of microscopic models that are available to describe the polymer behavior, and then specifically we will look at one simple model which is called the dumbbell model, and we will see that how, based on the microscopic mechanisms that we incorporate in the dumbbell model, we get a response which can be mapped back to the bulk rheological response for which we have already discussed in the course. So, beginning with the overall idea, we have discussed continuum picture throughout the course. When we set continuum picture, we said that the continuum is made up of material particles, and these material particles were uncountably infinite. Basically, between any two particles there are again infinite sets of particles, and because of the continuity of the field variables that describe the material particles and the attributes, field variables are the attributes for several material particles, we can then describe the overall relations between field variables using governing equations. And we saw that for rheometry, the mass balance and the linear momentum balance, or equation of continuity and equation of motion, were the two governing equations which can be used to solve all problems related to rheology. And so, when we look at microscopic picture, we recognize that matter is made up of discrete objects. So, therefore, we built in our model the discreteness of the objects, and again they are referred to as particles, but these particles could represent one of several things. For example, the particles could represent atoms, they could represent subatomic particles like electrons and protons, the particles could also represent molecules, or they could also represent the drops and colloidal particles for a multi-phase system. So, therefore, particle in this sense is a generic description of the basic building block of matter, and the key idea here is that we have discrete set of objects. So, in general we will talk of the material being described using, let us say, n particles, and so what these n particles do and how do they interact with each other or with surrounding will determine how the overall microscopic picture is defined. So, energy of each of the particle will be very important in terms of description of the system, and at the microscopic scale, since the particle moves about, it has a velocity, and based on its velocity it will have a kinetic energy, and given that the particle moves about and it interacts with the other particles, it interacts with the surrounding medium, it also may interact with a field such as electric field or gravitational field which is imposed on the overall system. So, therefore, there is a potential energy associated with each and every particle, and so the overall energy of these particles can be thought of at the microscopic scale being defined based on the kinetic energy and the potential energy of these particles. And so, the velocity and position therefore determine the energy of each particle. Velocity directly determines the kinetic energy itself. When we know the position of each and every particle, we know how they are interacting with each other, we know what is the relationship between position and the interaction with an external field such as gravitational field. For example, when we generally use the word potential energy in school and earlier, we are only talking about gravitational potential, and so when the distance changes, the potential energy changes, and therefore, we can talk about how the potential energy changes can be related to what is the gravitational force. So, similarly, in each case in the n particle system, given that we have multiple particles, how they are spaced with respect to each other will determine the overall potential energy. So, we have, let us say, a particle which we will choose to call ith particle, and surrounding this we will have several other particles. And so, what we have are interactions between these particles. So, these are all various interactions that can take place, and so our interest is in defining the overall potential energy based on these interactions. And the potential energy will be determined based on the distance between particles. Similarly, if there is an external field which is being imposed, for example, it could be an electric field, or we could have an external field which is, let us say, gravity, then in that case again the relative position of each and every particle with respect to, so the position of this particle and the position of this particle and the distance again will determine what is the influence of the gravitational field. And so, in general, distance between particles is very important. The overall arrangement of these n particles is also called the configuration. So, therefore, the arrangement of particles in 3-dimensional space is called the configuration. So, therefore, configuration is very important in determining the potential energy, because configuration, which implies the distance between various interacting particles, will determine how much is the interaction energy between these interacting particles. And so, velocity of the particle will determine the kinetic energy, and the configuration will determine the potential energy. So, therefore, to specify the overall microscopic state of each and every particle, we will need to define its velocity and its position. Now, velocity itself is vector, position also is a vector, and if we are describing them using a 3-dimensional space, then we require 3 velocity components and 3 position components. So, basically we require 6 variables, 3 components of velocity and 3 components of position to describe the state of one particular particle. Similarly, if we describe the state of all such particles, then we would have completely specified the configurational space of the particles, as well as we would have described the overall velocity of each and every particle. So, in general, to describe the n particle system, we need 6 n variables. 6 variables are required to specify state of one given particle. 6 times capital N variables will be required to specify the state of the system. So, you can see that the number of variables that have to be specified are exceedingly large. Remember, we are trying to use these particles in the microscopic picture to represent molecules and colloidal particles and drops and so on. And our aim is to actually use this microscopic picture to represent the material properties at the bulk scale. And we know that large number of molecules or particles and drops will make up the bulk of the material. We know, for example, that Avogadro's number 10 to the power 23 molecules are involved in 1 mole of material. Similarly, when we take a small drop of ink, the number of colloidal particles there is exceedingly large, 10 to the power 6, 10 to the power 8 per unit volume. So, therefore, we are talking about extremely large number of particles which generally make up the microscopic system, and therefore, the number of variables which are required to specify the state of the overall system is exceedingly large. We talk of this specification of state of the system in terms of phase space. So, just the way we have a 3-dimensional space and which describes physical space. For example, we could talk of, let us say, a rectangular coordinate system which is a 3-dimensional physical space, and I could ask the question that if I am looking at, let us say, position of a particle in this. So, I would say that the position of the particle can be specified by specifying the 3 coordinate systems x, y, z, and I could ask questions related to, for example, whether the particle is in some hypothetical control volume. I could ask the question also that what is the probability of observing the particle in this volume compared to, let us say, some other volume which is much larger. So, this is all the description in 3-dimensional physical space, and we require 3 variables, and therefore, this is a 3D space. Now, what we have seen is for a overall particle we require 6 variables to describe the state of the system. Since in this case we are only describing the system using a physical state, which means location, we require only 3D space. But if we have 6 variables to specify the state of a particle, we will require a 6D space, and therefore, the 6n variables which are required to describe the state of a system is called phase space. So, at this point what is helpful for us to know is the following, that to specify position we require only 3 variables. When we are trying to specify state of a system we require 6n variables, and unless we are able to specify the 6n variables we cannot specify the state of the system. Just the way here also, if we just specify x and y, there is a whole lot of possibilities of z, in fact infinite possibilities. So, just specifying x and y cannot specify the position of the particle. Similarly, when we specify the state of the system we will need to specify all the variables that are required to be specified, and these 6n variables are of course velocities and positions. Now, we could ask a similar question that for example, if this particle disappears from this position and appears in another position, then what we say is the particle has changed the physical state or it has changed its location. Similarly, in the phase space a system can be depicted as a point and then it can move from one point to another point in the phase space. So, system can move from one point to another in phase space. So, this is very analogous to the particle moving from one location in physical space to another location. So, therefore, we can see that there is an analogous description which is being used to describe physical space, which we are all very comfortable with, and we have solved many problems related to description of physical space and motion of objects in physical space. We have to imagine now a similar phase space in which the evolution of system takes place. When we say evolution of a system takes place, we imply that system moves from one particular state to another state through series of in between states, and so this is called the evolution of the system. So, now looking at the fact that there are very large number of particles, we necessarily require statistical measures to define various quantities which are related to the system. Given that the number of particles is very large, the specification of each and every particle is required. However, the description of the bulk behavior need not be related to the properties of each and every particle, but it is related on average to what the particles are doing. So, to understand this feature, one interesting observation that we make is the fact that what happens when there are very large numbers involved, and we can think of the phenomena of large numbers by just looking at a coin experiment. When we toss a coin, whether it is head or tail, the probability is just half. Now, if I throw two tosses of coins, then what happens is the probability of all heads. So, if I have two tosses, probability of all heads is 1 by 2 into 1 by 2. Similarly, probability of one head one tail is also half, and so the probability that in two tosses I will get both of them as heads or both of them as tails or one head one tail, all of these are equivalent. So, there is not a big difference between all of them being heads or one of them being head and one of them being tail. But if I do 10 such tosses, then the probability of all of them being heads is half into 10 to the power 10. So, this is now an exceedingly small number. So, what happens is when we do large number of trials, then we can quite often say that the number of tosses, if let us say in this case, if number of tosses is n, the probability that heads will be within 1% of n by 2. So, if I throw 100 tosses, if I do the coin toss experiment 100 times, 49 to 51 of them are heads. This probability is going to be higher and higher when n is larger. So, this probability is higher when n is larger. We saw that this probability is quite significant, but not it is equivalent to obtaining heads and tails, but as we go on we will see that the probability that we are 1% of n by 2 will be higher and higher. Similarly, the probability that all tosses lead to heads. So, this probability will be lower and lower when n is larger and larger. Again we saw that all tosses leading to heads, the probability was significant, but it will be lower and lower. So, the fact that large number of n is involved in the microscopic system of our description, this helps in terms of defining statistics which are relatively easy to deal with. So, if we have n very large number of coin tosses, we can generally say that the probability that the number of heads is between 1% of n by 2 is almost close to 1. So, therefore, we can generally assume that if there are large number of trials, we will get 50% heads and 50% tails. And similarly, the probability that all of them are heads, such probabilities can be, since it is exceedingly small, such events can be discounted. And when capital N becomes 100, 200, even with such numbers itself, we can get the statements that are mentioned here to be true. So, therefore, large numbers whenever they are involved, the statistics quickly converge to what is the expected or most likely scenario. So, in case of this coin toss experiment, the fact that half of them will be heads and half of them will be tails will be the expected scenario, and that is what we are most likely to observe in any trial as long as capital N is large. So, given this overall behavior of large numbers, it helps us in describing the continuum behavior as an average of behavior which is at the microscopic scale based on large number of particles. So, all the particles, they move about, they interact with each other, they interact with external fields, and based on their displacement, we could also talk of what is the average displacement at the bulk scale. So, for example, in the microscopic state, if we have the picture that we have a particle and these few sets of particles, if let us say the overall fluid is stationary, then we know that, for example, if I take a jar of water and overall the water as a fluid is stationary, we still know that water molecules are moving about. So, when we are trying to build a microscopic model for water, what we will do is we will say particles which are moving about. So, if I take a snapshot after a instant of time, what I will see is that the same particles would have moved in different locations. So, the particles which were in location 1 at one instance of time, an instant of time, have moved to another location another instant of time. Now, if I look at the displacement of each and every particle, so I can look at what each and every particle has displaced by. I can see in this case that this is one displacement, this is another displacement, this is another displacement, and if I have such a large number of particles and if I find the average, so displacement of each particle, and if I now find the average displacement, this will go to 0 because it is a stationary fluid and particles are going in random directions. So, clearly in this case what happens is the displacement of each and every particle is definitely not 0, but the average displacement is 0. In our course what we will deal with is rheological rheometric flows. So, for example, we may have a simple shear flow, in which case we have the top plate moving with certain velocities, and in this case again we have, let us say, certain particles and they occupy certain location again at one instant of time. Now, when we look at the same set of particles in another instant of time, what we will generally see is the fact that on average each of them get displaced with some So, in all cases if you try to resolve the displacement in y direction and displacement in x direction, what we will see is average displacement in y direction will be 0 and average displacement in x direction will not be 0. So, therefore, what we can see is whatever is the behavior of the particles at the microscopic scale, in this case the behavior is being described using displacement as a variable, the average displacement can be used at a bulk scale. Similarly, if we have a velocity of these particles, then the average velocity of all the particles can describe the bulk velocity. Again, for a stationary jar of water, the velocity of each and every particle which is representing let us say the molecules of water will be non-zero, since molecules are moving about. However, when we calculate the average velocity, that is going to be 0 because the overall fluid is stationary. If we now subject the same fluid to a shear field such as given here, then in this case we will again have an average displacement of particles which is over and above the random displacement which comes about because of microscopic interactions which happen between different particles. So, variables which are at the microscopic scale can be averaged to give us the bulk response. Now, when we have no deformation and no flow, we will have non-zero displacement and velocity for each and every particle, but we will have average displacement and average velocity of particles to be 0. Now, when we look at some other variables, for example energy. So, we discussed already that each and every particle has velocity and therefore kinetic energy. Similarly, each and every particle has a potential energy because it is interacting with other particles, interacting with external fields, and many of these interactions can be classified in several ways. For example, there could be quantum contributions which are related to electronic interactions which are related to bond vibrations and so on. There could also be classical interactions in the sense interaction between two charges which are electrostatic interactions. So, therefore, depending on the nature of interactions and depending on the interactions that are important for the system of interest, we have an average potential energy which can be described at the bulk scale also, depending on how each and every particle interacts with each other, and that is averaged to give us the bulk potential energy. Now, a similar question arises, given that in rheology we have discussed stress, strain and strain rates. Since velocities and displacement can be averaged out to give us the bulk displacement and bulk velocity, those are easy to calculate. What is meant by stress at the bulk scale? Given that at the microscopic scale each and every particle is interacting through these energies, we will make a hypothesis of forces which are experienced by each and every particle, and based on the presence of these forces and how the forces are exchanged across a hypothetical surface in the material, we will define stress. So, one of the key learning in this segment of the course will be as to learn what is the microscopic interpretation of stress. And so, the n particle system basically we have said evolves from one state to the other, and this evolution is based on dynamics of each and every particle. So, for all capital N particles we can write a governing equation, and in this case this is nothing but a linear momentum balance or Newton's second law, which says that mass into acceleration is equal to sum of all the forces on it. Now, the forces that each and every particle experiences could be different types. It could be the drag or friction which is experienced based on surrounding medium. So, quite often we use Stokes law kind of expressions to describe the drag force that is being experienced by a single particle. So, each and every particle has several forces which it experiences. So, in the next segment of the course we will first discuss some of these forces that are encountered by the particles, and then we will look at how do we try to simplify some ways in which we can analyze the system more easily.